Welcome to our video. For our project, we did an extension of the mechanization of Howe's method to include lazy pairs as an exercise in co-induction. This presentation will include the on-paper proofs alongside the mechanizations of them in Beluga.
Induction is a well-understood and trusted form of argumentation that is taught in all introductory computer science and math courses. In terms of functional programming, finite or inductive data is defined using constructors and analyzed using familiar pattern matching, while infinite or co-inductive data is defined by the observations that we can make about it using co-pattern matching. However, co-inductive reasoning is less widely taught, understood, or trusted. As explained in the practical co-induction paper by Cozen and Silva, 2016, proofs relying on co-induction still end up essentially reasserting the principle of co-induction every time it's employed.
So we want to be able to say that two programs have the same behavior when we add in our new data type of lazy pairs. It's hard to reason about program equivalence since it requires that we quantify over every possible context. So we formalize this idea of equivalence with the notion of bisimilarity. Now let's see what Emily has to say about what bisimilarity actually is.
Classical bisimulation proofs are examples of arguments using co-inductive reasoning. For instance, given two co-inductively defined streams, bisimilarity asks whether these streams are observationally equivalent. Two terms m and n are bisimilar if whenever m evaluates to an observable, so does n, and all subprograms of those are also bisimilar. For instance, for infinite streams, streams S1 and S2 are bisimilar if the heads of the two streams are equal, and the tails of the two streams are also bisimilar, meaning that all observations that can be made about the two streams are equivalent. Our goal is to extend a case study on co-inductive proofs involving Howe's method, which originally involved the call-by-name lambda calculus extended with lazy lists, as defined in the Pitts 1997 paper, to include an additional data type, namely lazy pairs, both on paper and mechanized in Beluga.
Our goal is to show that applicative bisimilarity is a congruence, even after we add lazy pairs. So we focus on proving that applicative similarity is a precongruence, and we do this using Howe's method, which we'll see later. And then bisimilarity can be arrived at from symmetry. Why can't we directly prove the precongruence of open similarity? Open similarity is just applicative similarity extended for open terms by substitution. This is because it is difficult to prove that we can replace any part of a program by one that we already know is equivalent, as stated before. So this is where Howe's method can help.
Since a direct attempt to prove precongruence of open similarity breaks down, Howe's idea was to introduce a candidate relation, the Howe relation. On screen we see how the relationship is defined, and as it turns out, it is much easier to show Howe's relations of precongruence. From there we prove m and n are in Howe relation with each other if and only if m and n are an open simulation of each other, thus showing open similarity is also a precongruence. In our project, we extend this technique to lazy pairs. We give the extension of the Howe's relation to lazy pairs, and extend relevant proofs to show it is still a precongruence and coincides with open similarity.
We extend the Howe's relation to pairs using the following inference rules. We also borrow the evaluation rules from Pitts 1997. In order to show that the Howe's relation extended to pairs still coincides with open simulation, we will be going through the same proof structure presented in the paper.
This involves extending applicative simulation to lazy pairs, and showing applicative similarity remains reflexive, then extending the definition of a compatible relation, and last but not least, showing Howe's relation coincides with open similarity by proving the sublemata, then concluding with the main theorem. Now we will discuss the proofs of these lemata.
Lemma 1 is semi-transitivity of Howe's relation, which says that if m and n are related by Howe, and n and L are related by OpenSim, then m and L are related by Howe. The proof of this is by the transitivity of open simulation, and then by the definition of Howe relation. Lemma 2 is the reflexivity of Howe's relation. This is by induction on the typing derivation, and the proofs the cases of the proof generally follow the structure of appealing to the induction hypothesis, using the reflexivity of open simulation, and they use the Howe's inference rules to reconstruct. Lemma 3 says that the Howe relation is compatible. So we start by extending our definition of compatibility for pairs, and then the proof follows pretty immediately by the reflexivity of open similarity and using the definition of Howe relation. Lemma 4 says that open similarity is contained in Howe. This proof is immediate by reflexivity and semi-transitivity.
We now show substitutivity of the Howe relation. Suppose we have gamma proving that two terms m1 and m2 are Howe related at the type tau, and we also have psi proving that sigma 1 and sigma 2 are Howe related at the type gamma, which means that sigma 1 and sigma 2 provide well-typed simultaneous substitutions for variables in gamma. Then we want to show that psi proves that sigma 1 applied to m1 still Howe relates at the type tau to sigma 2 applied to m2. The proof proceeds by induction on the derivation that m1 and m2 are Howe related at type tau. The proof is then completed by applying the induction hypothesis on the premises of the Howe derivation, using closure under substitution of open similarity, definition of substitution, and finally the Howe inference rules to reconstruct the fact that m1 and m2 are still Howe related at type tau after applying the substitutions.
In Lemma 6, we're going to be showing that the Howe's relation still mimics simulation conditions when we extend it to pairs. And this means that given a pair m1, n2 Howe's relations with n, we have that if n that we have n evaluates to a pair p1, p2, such that m1 Howe's relations of p1 and m2 Howe's relations of p2. The proof is done by inversion on the Howe's relation. For Lemma 7, we show that the Howe's relation is downward closed, and this just means that if we have m Howe relations with n, and we know m big step evaluates to v, then v is also in a Howe's relation with n. This is done through induction on the evaluation, as well as inverting the Howe's relation and by using applicative similarity of the Howe's relation.
The eighth and final lemma to prove says that Howe's relation coincides with applicative simulation for closed terms. The proof is by co-induction on the derivation of the Howe's relation. The only case we need to add is the case where the derivation of Howe's relation ends with the H-pair rule.
The proof of this case uses Lemma 7, downward closure, Lemma 6, Howe mimics simulation conditions, and appeals to the co-inductive hypothesis before constructing the applicative similarity derivation made possible by its compatibility.
Having proven all these properties are satisfied with our extension, we are ready to prove the main result, where gamma entails P is in Howe relation to Q if and only if gamma entails P is in open similarity with Q. Similar to the original paper, right to left is immediate from lemma 4, and left to right is a proof by induction on gamma, using 8 for the base case and closure under substitution for the step. It turns out we have nothing to extend here, as the step case deals with an arbitrary instance of the Howe's relation. Since the extension of pairs satisfies all desired properties, this proof still holds without modifications. Finally, we conclude with our main goal. Open similarity, extended to support pairs, is a precongruence.
All the extension of the proofs seen in this video have also been mechanized in Beluga, so you can check that out in the Beluga file on our GitHub. Thank you for watching our video.